Descend a few hundred meters below the ocean's surface, and the sun completely disappears. You enter a world of absolute darkness. Down here, animals do produce their own light through bioluminescence, but water scatters those photons so rapidly that glowing signals are only visible from a few meters away. Because humans navigate our world primarily through sight, we looked at this impenetrable blackness and assumed the deep sea was a silent, empty vacuum. Our reliance on sight limited our perspective, obscuring a world that operates on an entirely different sensory axis. In the 1990s, scientists began dropping advanced hydrophones into the water. The audio they captured was deafeningly loud. This line chart shows the frequency over time for an acoustic anomaly recorded in 1997. Notice the massive spike and rapid rise in pitch. Researchers nicknamed this sound the bloop. It was powerful enough to be picked up simultaneously by multiple sensors placed over 5,000 kilometers apart. Soon, the network detected other anomalies. Look at what happens when we add the audio data profiles for a 1999 recording named Julia and another called the Biodeck. They display strange, almost mechanical acoustic shapes that defied any known biological classification. The bloop, for instance, registered at a volume significantly higher than the calls of a blue whale, which holds the record as the loudest known animal on Earth. Researchers had to figure out exactly what produces a noise louder than a whale and how a single sound can survive traveling unbroken across an entire ocean basin. The answer starts with basic physics. Because water is much denser than air, sound waves travel through it about 4 times faster, and they carry their energy much further. This diagram highlights the so far deep sound channel, where temperature and pressure minimize sound speed. Changing water density physically traps low-frequency waves, bending them away from the surface or floor. Without spreading vertically, a single pulse can bounce thousands of miles across the Pacific. The SOFAR channel acts as a global acoustic superhighway, linking marine environments that sit on opposite sides of the planet. An enormous amount of biological traffic relies on this superhighway. Huge colonies of tiny snapping shrimp create a localized crackle so intense it can actually hide the acoustic signature of a passing military submarine. Entire coral reefs broadcast distinct acoustic signatures into the surrounding water. Migratory fish memorize these specific frequencies to navigate their way back to their exact birthplaces. When scientists realized how far sound could travel, the massive origins of the Bloop and Julia recordings finally made sense. They were the acoustic signatures of polar ice quakes and grounding icebergs disintegrating off the coast of Antarctica. Another seasonal noise known as the upsweep was traced to underwater volcanic activity in the South Pacific. And in 2014, biologists finally matched the bizarre mechanical quack of the bioduck to the actual calls of the minke whale. These anomalous sounds were the natural physical and biological processes of the planet, broadcasting on a frequency we hadn't decoded yet. Acoustic technology has revealed the seafloor as a densely packed landscape of information. Today, deep-sea surveillance relies on vast integrated networks of military and scientific hydrophones anchored miles below the surface, constantly recording the SOFAR channel. Researchers are deploying artificial intelligence to sift through decades of these massive, unorganized sound archives, picking out patterns human ears could never catch. By analyzing distinct sound profiles, scientists can actively track the unseen migrations of marine life across hemispheres and monitor the overall health of deep-sea ecosystems. This exact same audio network detects planetary-scale physical events as they happen in real time, from the shifting of deep tectonic plates to the structural collapse of polar ice shelves. The ocean will always remain shrouded in darkness, but by intercepting and translating its acoustic language, we can finally map the life within it.